This is part 2 of the rivets and bolts subsection, and at the end of part 1 we were talking about our single shear joint here, a nail going through two 1-inch boards. Let's say that in the left board the distance between the nail head and the pivot point is y inches. Okay, there's our pivot point. This nail is rocking like this because this board's pulling down, this board's pulling it up. And this force down, if you were to cut this nail and replace it with somebody just trying to push it down, it would be pushing the nail against this wood. But this wood over here holds this end of the nail down. So the nail is pivoting. Here's the pivot point. It's closer to the left side than it is to the right side. It has to be somewhere on the left side because the stress between the nail and the wood is proportional to how far the nail is pushing the wood. And with the pivot point over here, the nail's not going to push the wood as far here as it is pushing it here. Okay, so we're going to call this y inches. We're going to figure out how far it is. We're going to find out where this pivot point is. We're calling this y inches. Of course, it's only part of an inch because this is a 1-inch board. We're going to call this distance from the pivot point to the right side of the board 1 minus y. Okay. Obviously the other board, this right board, it's in a similar situation. Whatever you see over here, you see over here. It's a mirror image. Let's say the left board is being lifted with a force of F1. There's our F1, that's what's holding up the left board. And the right board is being pulled down with a force of F2. Well, F1 is going to equal F2 because you have to pull up as much as this is pulling down. You put a 10-pound weight here, you're going to have to lift 10 pounds. Make it 20 pounds here, you have to lift 20 pounds. This is assuming that the wood and the nail are weightless, of course. Actually, F1 would be just a little bit more than F2 because F1 has to lift all this also. The shear force in the nail where the two boards meet right here, it's also equal to F1 and F2 because that nail is what's holding it together. If you were to saw that nail in two, well, this board would just go down, that one would go up. Okay, the shear force pulling down on the nail between the two boards and the bearing force of F3. Okay, the shear force that this nail in this board is pulling down this other half of the nail in this board. That force plus F3 equals F4. F4 is the force that's between the pivot point and the right side. Okay, so you could say that F1 plus F1, which is the force in here, you could say F1 plus F3 equals F4. The wood where the force F3 exists, which is between there and there, the nail head, the left side of the board, and the pivot point, is pressed more against the nail at the left side of the board. In other words, it's pressing more against the wood here than it is here. It's not pressing at all here, that's the pivot point. It's pressing half as much here, but it's pressing most of all here. As far, comparing it from there to there anyway, it's pressing more here than any other place between here and there. Over on this side it's pressing here much more than it's pressing here because this is longer. Okay, no stress exists at the pivot point because wood's not pushed up or down at this point. The force vector F3 represents all the force of the wood onto the nail between the nail head and the pivot point. If we were to look at all these little incremental units of area between here and here and just get one vector to represent them all, we would call it F3 and we'd have it there. And it would be closer to that side than it is to the pivot point because we have more force toward this end, because we have more stress toward this end. F3 is closer to the head of the left side of the nail than to the pivot point because wood's compressed more at the left edge. Okay, figuring out where F3 is along this line, is like figuring out where the center of gravity of a triangle is. Here we have us a triangle that looks kind of like the way our left side of our pivot point looks, because the nail's pushing up here at the edge. That's what this high part symbolizes, and right there the nail's not pushing the wood at all, so there's no stress at the pivot point, maximum stress at the left edge. Okay, so to figure out where the center of gravity of this triangle is, there are two different ways we can do it. We can draw a line from the vertex, from any vertex, to halfway across its opposite side. Do that again with another vertex, or do it with all three vertices. And these lines intersect at the centroid, which is where the center of gravity would be if this triangle were uniform. In other words, if it weighs the same per square inch over here that it weighs over here. Okay, so another way we could do it is we can draw a line parallel with each side. See, here's a line parallel with this hypotenuse. Here's a line parallel with this leg. Here's a line parallel with this leg. If we draw them 1/3 of the way from the side that they're parallel to the vertex opposite, those lines will intersect at the centroid. Okay, an incremental sliver of this triangle, right here I went ahead and drew an incremental sliver. Here's a little bit of surface area. Well, actually this is a length, but you multiply this length times the diameter of the nail, you have your bearing surface area. So we'll just think of this as representing our incremental surface area times the stress. Area times stress is going to give you an incremental amount of force. Okay, an incremental sliver of this triangle represents an incremental bearing surface area multiplied by the stress at this particular area, which is an incremental force between the board and the nail at this area. A multitude of these incremental forces from the left side, from here to the pivot point, well, to the right vertex of this triangle, same thing, would balance about the center of gravity, which is going to be around there, or the centroid of the triangle. Now, we don't want to be confused here and think that the line that divides the area in half is where the center of gravity is. The line that would divide this area in half would be square root of 2/2 times this distance, or 0.707 of the distance from here to there. But the center of gravity, it's going to be 1/3 of the way from there to there, or 2/3 of the way from here to here. So 0.333 instead of 0.29 something. Center of gravity is going to be a little more that way than the line that divides the area in half, because you have so much of this sticking out further from the line. You have to move over to get where the center of gravity is. Getting back to our nail boards, we can say that F3, the force vector that represents all the incremental forces between the nail and the wood, between the left edge and the pivot point, is located 1/3 of the way from the left edge. In other words, from there to there, F3 is going to be 1/3 of that distance. So that'll be 2/3 from there to there. That'll be 1/3 from there to there. Why? Because the center of gravity of this triangle is 1/3 of the way from this base of our triangle up here. And the forces acting between the nail and the wood are like all these little incremental slivers of force on our triangle. You know, the little incremental units of area times the different stresses. And they would balance at this 1/3 point. So our F3, which represents all these little incremental forces, would be 1/3 of the way from there to there, pushing down, because the nail's pushing up on the wood's pushing down on the nail. Okay, the position of F3 is Y over 3 to the right of the left edge. Okay, 1/3 of that, that's Y, so it would be Y over 3 from there to there. The position of F4 is 1/3 of the way from the right edge. There's F4. See, F4 represents always forces between the pivot point and the right edge. It's 1/3 of the way from the right edge, the edge where the most stress exists. It's not 1/3 of the way from here to there. Wouldn't be right there. It'd be 2/3 of the way from here to there, right there. F4 is 1/3 of the way from the right edge of the board to the pivot point. F3, the force vector that represents the force between the nail and the wood left of the pivot point. F4 is the force vector that represents the wood between the nail and the wood right of the pivot point. And F1 is the shearing force of the nail between the two boards. Okay, we drew us a little teeter-totter here to represent all these forces. There's F4, it has to lift up enough to support the weight of both F1 and F3. So we're going to let it be like the fulcrum of our teeter-totter. F1 is much greater than F3 because F3 is so far away from F4. F1 was right there at the right edge of our board. There's where F1 acts. There's where F4 pushes up, and there's where F3 pushes down. Okay, F3 is comparable to the weight of a small person on one end of the teeter-totter. See, he's kind of skinny. F1 is comparable to the weight of a large person on the other end. F4 is comparable to the force of the fulcrum pushing up. It's like this is baby bear, this is daddy bear, and this is a real strong guy lifting the teeter-totter in the middle. So let's say the small person on the left end of the fulcrum weighs 50 pounds. We'll call him 50 pounds here. And is 4 feet from the fulcrum. Right there, 4 feet. The 200-pound person on the right end balances him if he's seated 1 foot away from the fulcrum. See, 200 pounds, if he's 1 foot away from this fulcrum, he'll balance this 50-pound guy who's 4 feet from the fulcrum. If the teeter-totter is weightless, the fulcrum lifts 250 pounds, because 200 plus 50, that's what he has to lift there to support them all. As we can see, 50 pounds times the 4 feet to the fulcrum equals 200 pounds times 1 foot to the fulcrum. If we look at the forces times their distances to any given point, they always balance out, regardless of where that point may be. Let's look at the forces times their distance from the left end of the fulcrum, right here. Okay, the 50-pound person is 0 feet from the left end. See, he's sitting right on the left end. So his force times distance is 0, because his force is 50 pounds and his distance is 0 feet. So that's 0 foot-pounds. The fulcrum's 250-pound force is 4 feet from this left end. So we have 250 pounds pushing up times a distance of 4 feet. So that'd be 1,000 foot-pounds. Okay, 1,000 foot-pounds trying to push this teeter-totter counterclockwise about this point. The 200-pound person's weight times his distance of 5 feet from the left end. See here, he is 200 pounds. There's 1 foot. There's 4 more. He's 5 feet from the left end. It equals 1,000 foot-pounds and balances the system, because that 250 times 4 equals this 200 times 5. Well, I don't think we have enough time. In our next lesson, we'll use a reference point a mile away and see that it still balances out. But we'll catch that in part 3.